Good morning, everybody. Glad to see you all here this morning for another program of Coronado Roundtable. I'm Christian Escobar, the president. So we have a great program. This morning, we will have Dr. Neil Farber speaking about a very interesting subject that we will have the introduction for in just a few moments. But if you will please stand, and we will pledge the allegiance to the flag. I
pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
As you know, our programs are recorded live for Zoom, and we apologize for the technical problems we had last month. But among other corrections, we have from the library new microphones, so that will be a great improvement along with other things that have been changed. So we'd like to thank the Coronado Library for those improvements, and thank the staff, including Selena Ayagulid and at the back at the table. For those of you at home, if you could please mute your computer or device, and please turn off your camera. You can use the chat box feature for the question and answer portion of this program. For those of you in the audience here, please silence your mobile phone. And if you have problems hearing the program, please raise your hand and say so. Our coffee this morning is offered by Namalo Brew, the coffee cart in front of the library. We do ask for a $3 donation to make that feasible, and we appreciate your donation. Our speaker is Dr. Farber, who will speak on this subject, as mentioned here on the screen, astrobiology, the search for life on other worlds. Our own Coronado Roundtable Board Member Emeritus, Rear Admiral Steve Clary, will be providing the introduction. Steve, would you please come forward? Thank you. Thank you.
Well, good morning, and thank you, Christian, and thank you for your continued leadership here on the Coronado Roundtable and here in Coronado after your many years of building this library into one of the best in Southern California.
Thank you.
In addition to being a board member here of the Coronado Roundtable, I am also on the advisory board of the Osher Lifelong Learning Institute at UC San Diego. It is a more comprehensive lifelong learning experience that we offer here at the Roundtable, and we offer lectures twice a day, including the annual Vice Admiral Charles Martolio Memorial Lecture.
Not the memorial part yet.
We offer classes twice a day with no grades, no tests, no homework, and I should mention that Mike as well, also been one of our speakers. And as you'll hear in a minute, Neil is a regular. We certainly, there are no grades, no tests, no exams. We welcome you all to our open house on 28th June. And here at the Roundtable today, we feature one of the Osher Institute's popular speakers, Dr. Neil Farber. A notable UCSD cosmologist, not a cosmetologist, a cosmologist, recently asked, have you ever looked up at the night sky and wonder if anyone is looking back at you?
Yes.
And that is the subject of Dr. Neil Farber's lecture today.
Excuse me, I'm sorry.
Not a bit. Not a bit.
Welcome. Always glad you're here, Carol. Thank you.
Neil Farber is a retired internal medicine specialist from UCSD Health. Moved here from Philadelphia. I retired from practicing medicine in 2019. And he says he's always been interested since childhood in space. So after retiring, he joined the Air and Space Museum as a docent, where he leads tours on Mondays and Fridays. And he also became a NASA Solar Systems ambassador. And he is here today in that capacity, lecturing at the museum, local communities and schools throughout the area, and YouTube videos on a wide variety of topics. Neil, delighted to see you with us today. Thank you so much for coming.
And can we turn down the lights? Here. Because some of these slides are going to be quite interesting if we can do that.
Draw the shades in the back, that helps.
So this is one of humankind's primary questions. Are we alone in the universe? And I find this topic really fascinating. I was a biology major in college, an internal medicine specialist for 40 years. So life has always meant something to me. But I always wondered, is there life elsewhere? And we're not talking about necessarily just intelligent life. We can talk about any kind of life. And I'll give you this sort of spoiler at the beginning, okay? No, we haven't found any intelligent life anywhere, including Earth. But we're looking, and I'll talk about that briefly. And then any type of life, we haven't gotten to the point where we can have it in our hands and look at it. But I will tell you, we're getting really close. And my prediction is within the next 20 to 30 years, we will be able to definitively say there is life elsewhere. Okay. Now, if that didn't blow your mind, I have some slides that will. So in terms of intelligent life, the way we're looking for intelligent life is something called SETI, which is the Search for Extraterrestrial Intelligence. And this uses radio telescopes looking for repeated signals or signals in patterns. And so far, we haven't found any positive findings, at least not as yet. Well, what about any other life? So that's it for intelligent life. That's all I can say. It's up in the air. And I know a lot of people are going to say, what about the UFOs, et cetera, et cetera? No definitive proof yet. In terms of other life in the universe, we don't, as I said, we don't have direct evidence. We haven't been able to have something in our hands that we can look at and say, this is life. But there's some biologic signatures that are being sought. And you'll see that we're getting very close in terms of that. For example, if a planet has carbon dioxide in it, that can be a natural occurrence. And Venus has lots of carbon dioxide. And there's no life on the surface of Venus. We'll get there. But evidence of carbon dioxide could potentially be indication of potential life. Certainly oxygen in an atmosphere is definite evidence for at least plant life. We haven't seen that anywhere yet. And the other thing we're looking for is certain organic molecules. And I'll talk about that. And the other thing we can do is look for habitability. That is, does a planet have everything necessary to have life on it? And the three things you need is persistent liquid, either water or something else. We look mainly for water because that's what we have here. But we look for other liquids as well. And I will say that originally, so when we're looking for liquid water, we can, if we're looking at other stars, planets surrounding other stars, we can only look on the surface. But in our own solar system, we're looking not only on the surface, but underneath the surface as well. You also need key chemical ingredients for life. So carbon, oxygen, nitrogen, sulfur, phosphorus. I think I named them all. So we're looking for those. And then energy for metabolism. There has to be some kind of energy. It doesn't have to be a star or the sun. There's other kinds of energy. We'll talk about that. So we're looking in two areas. One's at distant stars, meaning exoplanets, that is planets around a distant star. And we're looking in our own solar system at not only planets, but certain moons as well. So let's talk first about distant stars. There are about 100 billion galaxies in the universe. Some say even more than that. Some people are saying, some scientists are saying up to 1 trillion galaxies in the universe. And there's about 300 billion stars in Milky Way. And the Milky Way is a largish, but kind of average largish galaxy, which means that there's at least 3 times 10 to the 22nd stars in the universe. That is 3 times 10 with 22 zeros after it. Okay, there's no term for this. It's basically more than all the grains of sand on Earth. You take all the grains of sand in the ocean, in the deserts, everywhere, and put them all together. There are more stars than that. So there's a very good possibility of life elsewhere, including even intelligent life. So far, all we have found is 5,500 exoplanets that have been discovered. So you see, we're only taking a tiny, tiny fraction of all that's out there. So how do we find exoplanets? There are 3 ways. There's radio velocity, transit, and direct imaging, and I'll talk briefly about these. So radio velocity uses Doppler shift, that is the shift in light instead of sound as something is approaching you and going away. This only gives us the planet's mass, and there's no information about its atmosphere. So if you see the planet that's here orbiting this star, it pulls on the star. And so the star wobbles, and you can see that wobble. And that tells you there's a planet there, how close it is, and how big it is. Okay, but you can't tell anything about the planet itself other than that. So we can sometimes find a planet that way, but to distinguish what it is, we need to look for either transits or direct imaging. Transits means that there's a change in brightness as the planet goes around this and passes in front or behind its host star. At best, the dip in brightness is only 1%, but NASA has some telescopes up there in space that are so sensitive they can pick up that change. So it gives us how big the planet is, where it is, but now also using spectroscopy, we can actually see what's in the atmosphere as well. So if you look, as this planet gradually gets in front of the star, it casts a shadow. And that means the brightness of the star dips. And NASA's Transiting Exoplanet Survey satellite can pick this up. And as you see, this dip in one is only 0.03%, okay, or point 3%, less than 3%, less than 1% of the dip, and yet it's able to pick it up. And then the best way is with direct imaging. And that is you take a photograph of the exoplanet, and you can use spectroscopy to see directly what's on that planet's surface. But there's a problem. Imagine, for example, so you have a sun-like star, and you have a hot Jupiter exoplanet. That means it's about the size of Jupiter, but it's hot. So it's close into the star. Or you're looking really, and so that wouldn't have life on it. What you're really looking for is an Earth-like exoplanet. Well, the equivalent would be if you have a lighthouse and you're trying to see that something near it, like a firefly next to that lighthouse. Okay? It's 1,000,000 times fainter than the lighthouse itself. Then you go to bioluminescence, which is 10 billion times fainter. It's impossible. And the answer is no, it's not. Because NASA has now things like, for example, the James Webb Space Telescope that has a coronagraph, which basically creates sort of an artificial eclipse. It blocks out the sun around that other star, blots out the light from that other star, so that you can see the planets. And you see here 1, 2, 3, 4 planets orbiting this star. And you can definitely see them, pick them up, and you can see what's in their atmosphere. So as I said, we've discovered over 5,500 exoplanets. Next, you have to do planet characterization, meaning does it have an atmosphere? What molecules are present in that atmosphere? Could it support life? That's the level we're at right now. The next level is, does it have life? And to be able to say, does it have life, we have to have direct evidence, which we don't yet. But we're getting close. So one of the things we can do is look for a habitable zone around a star. So a lot of times, astronomers will call this the Goldilocks zone, because if it's too close to that, if that planet is too close to the star, its surface is too hot. If it's too distant from that star, its surface has no liquid water. Now, these are exoplanets we're talking about, not in our own solar system. But we have found several hundred planets that are in the habitable zone, that is the Goldilocks zone, or the area where it's just right. It's not too hot, not too cold, liquid water on the surface could exist. And then we have found one planet that has carbon dioxide on the surface. None with oxygen so far. But it gets even better in a minute. I'll tell you about that. So we're talking about, as the star is hotter, the habitable zone is further out. If it's cooler, the habitable zone is closer. So one system that hasn't been intensely looked at yet is the TRAPPIST-1 system. And you see there's 4 planets that are in the habitable zone, 2 that are very much in the habitable zone. And these are rocky planets, meaning they could support life. But we haven't looked there yet. In our own solar system, Earth is the only planet that is directly in the habitable zone, but there's caveats to that, and we'll talk about that. So this is one of the interesting things about this one planet that's out there around another star. This was found by the James Webb Space Telescope. It's called planet K2-18b. It's about 120 light years from Earth. It's in the habitable zone of a star. And we know that it's a water world. It has lots of liquid on its surface. Okay. And more recently, this molecule was found in its atmosphere. This is dimethyl sulfide. Now, that James Webb Space Telescope found only a trace, but another telescope on Earth found about 1,000 times the amount in this planet as you could find on Earth's atmosphere. What does that mean? Well, dimethyl sulfide happens only in biologic life on Earth. That is marine algae, plankton, certain bacteria. So as long as we can research this and find no other inorganic way of making dimethyl sulfide, that means that planet has to have organic life in its surface. We're getting close to that. Okay, then what about our own solar system? One place to look is Mars, because there's possible evidence of previous ancient life. We haven't actually found it yet, but there's some clues that are being given to us that say that Mars might have had life in the past, might still even have life now. There's habitability in other bodies that we'll talk about, although there is no actual life yet that we can say. So the early rovers had a suggestion that there was water on Mars. They found outflow channels, these layers of rock that are sedimentary, which happens on Earth in water. And so Curiosity actually confirmed the presence of water. And it was present for about 1 billion years, from about the existence of Mars up until maybe 3 billion years ago. So 1.5 billion years of the possibility of water. And that was around Gale Crater. Oops, sorry. That was around Gale Crater. And Perseverance, the next rover, confirmed the evidence of water around Zero Crater. And I'll show you the evidence in a sec. But we're pretty sure that Mars was habitable for a long period of time. Now, when I was in high school, I remember being told that life on Earth didn't start until about 4 billion years ago, right? Which would mean there wouldn't have been enough time for life to have started. We now know, actually, that life started on Earth about 400 million years after the Earth was formed. So plenty of time on Mars for life to have formed. The findings of Curiosity were that, first of all, the surface around the landing site is made of these pebbles, and they're all sedimentary. There were all these rounded pebbles and sedimentary in nature. Many of the rocks are, as I said, are rounded, and the erosion is due to liquid water. So that indicates the probability of liquid water on Mars. And then further away still, there's this extensive sedimentary system that's seen, including basically molecules that basically only form in water. For example, variations of iron that are particular to water-based areas. These areas were low in salinity, so there was salt, but not too much, and a neutral pH, so allowing life to form. And it was a habitable environment, relatively young. It's entirely possible life could have started on Mars. The other findings, interesting enough, again on Mars, are that the building blocks of life were all there: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and there were organic molecules present, including complex carbon-based molecules. We don't know which ones because we don't have spectroscopy on these rovers that is as sensitive enough as the ones on Earth. We know they're different molecules, but we don't know exactly why. So it means two things. These could have happened naturally, or they could be biologic in origin. So if you look at this view from Curiosity, looking out, you can see that there's all these layers. And this is clear evidence of previous water because it's all sedimentary. The other thing is there's a clay-bearing unit. Again, that would be indication of water. And hematite-bearing units, which forms only, again, in a water environment. So we're clear that Mars had water, lots of water on its surface and was warmer in its past. The question is, did it actually form life? Again, these rounded pebbles, all near the landing site where Curiosity was. And in Perseverance, that landed in February of 21 at Jezero crater, it clearly was a river outflow channel and delta, and that's the best place to look for ancient life because of the fact that as it comes down off the mountain, the heavier stuff gets deposited as silt, and silt can contain organic material, i.e. life. So Perseverance has been drilling core samples, placing them in titanium tubes. Why? Because eventually they'll be brought back to Earth. This is one of the most amazing ones where they drilled. This is called Chayava Falls Rock. And there are all these things on it that look like this. What does that look like to you? To me, well, no, it's bigger than that. It's bigger, but it's not microscopic. This looks like either a bacterial colony or mold, right? This, it's like a moldy rock. Well, that's life. If we bring it back and look at it under a microscope, and that really is either bacterial mat that's extinct or mold that is now extinct, that was life at least once on Mars. So the future mission is, as I said, Perseverance are collecting these core samples. In the 2030s, a return mission is planned. And this lander will land next to Perseverance. Perseverance will trundle over and put the samples that have been collected in those titanium tubes into a return capsule, and they'll be returned to Earth for study. And the plan is to determine if those organic molecules are biologic in origin. So let's go to other bodies in the solar system. Now, we're getting a little far out, but not that far out yet. And literally far out, but also figuratively far out. Other planets or other bodies we'll talk about might have free water. They're not in a habitable zone. They're either, in Venus's case, they're too hot. Most of them, like Jupiter and Saturn's moons, are too cold. There's not enough energy from the sun, but they do have chemicals needed for life. So Europa is one of Jupiter's largest moons. It has an ice crust about 7 miles thick. Okay, it's pretty thick, but that's a whole planet size. So it's not that thick. But below that ice crust, there's an ocean that's about twice the size of Earth's, or all of Earth's oceans combined. It's way out of the habitable zone. but it has this liquid ocean, so it has to have energy. And the other thing that we're seeing is plumes of water that spray out through these cracks in Europa's crust. And it does have a rock mantle, so plenty of minerals that are needed for life. If you look at Europa, it's all these ice like cracks and whatever. But also, you notice all this schmutz, right? There's all kinds of material on the surface. Because otherwise, if it was just ice, it would all be just white. This is all stuff that's blown out through those plumes of water and settles back on the surface. Now, we don't know exactly what this is made of, but it could be not only the mantle, there could be carbon-based material on the surface. And if there's carbon-based material on the surface, there's carbon-based material in the ocean. As I said, the reason the ocean is twice the size of all of Earth is because there are no continents. There's the mantle here, but below the ice crust is all water. And so that's about, instead of 7 miles thick, this is about 200 miles thick. So if you look, Earth is not a water planet. It's a rocky planet. This is all the amount of water compared to the size of Earth. But if you look at Europa, you see that the amount of water is almost as big as the planet itself. So lots of water to be able to possibly support life. How does this happen? How do you get this sort of liquid mantle and liquid water? It's called tidal heating, okay? I want you to do something for me, both here and at home. I want you to wave your hands around like this. And all you feel is like a little breeze, right? Now, what I want you to do is do this, or you can rub your hand on your shirt or your pants. You do that, and all of a sudden, your hands are getting warm because of friction. That's what's happening in Europa and other planets too, other moons too, that we'll talk about. But you see it, sorry about that. You can see, basically, it's flexing. I can't do that, no. It's flexing, and so as it flexes, it heats the interior of Europa. And that's what allows for the energy and the liquid water. Now, this is a video of hydrothermal vents on Earth. These are at the bottom of the Pacific Ocean. So this is 5 miles down. There is no light. There is no heat. It is near freezing. But you see these vents spewing out this stuff and heating the area around it. And what are you seeing? Life. And I will tell you that of all the thousands of species, and there are thousands of species, of algae and bacteria and higher organisms, meaning tube worms and crabs and clams and things like that, of all of them, about a third of them have no connection to anything else on Earth. Now, does that mean these are aliens? No. What it means is that life formed down in those trenches, down in those hydrothermal vents, around those hydrothermal vents. And if it could happen there, it could also happen at Europa because it's the same conditions. So NASA has developed a mission to go look. This is Europa Clipper. It launched in October 24, so last year. It'll take 6 years to reach Jupiter. It will orbit Jupiter, which swings around Europa to avoid the high radiation. But it'll do 50 swings of Europa, and each swing will be targeted to go right straight through the middle of those plumes of water that are being sprayed up, so that we'll know what's down below. Its mission is to determine definitively if Europa is habitable. It's quote unquote not meant to determine if there is actual life. This is a wink wink, because if you talk to some of the scientists at JPL, they'll go, yeah, right. They want to find out if there really is life there. I don't know if we will, but that's one possibility. It's also going to look at the consistency of ocean, not only by radar, but by spectrography. And look at possible sites for future landers. Another planet is, another moon, I should say, is Ganymede, which is Jupiter's largest moon. It has a huge ocean underneath its ice shell, way, way bigger than even Europa. And it abuts rock. But you don't see all the schmutz on it because there are no cracks, there are no plumes of water coming out. So we don't know if it has any energy below. It really, truly is an ice planet, or ice moon, I should say. But you see, based on radar data, we know that the ocean is huge, but it may not harbor life because there's no energy that we could think of that would provide that, except for the tidal heating. So we don't know. As I said, there's no plumes of water, there's no organic material on the surface like Europa. So NASA doesn't have a mission currently scheduled to go there. Titan is Saturn's largest moon. It's far beyond the habitable zone, but similar to Europa in some ways. If you look at Titan, it's similar to Earth in some ways. Its atmosphere is nitrogen, just like it is Earth. Remember, Earth's atmosphere is 80% nitrogen. Okay, Titan is even more than that. The pressure is about 1.5 times that of Earth, so it's not a terribly high pressure environment on the surface. But whereas Earth's average temperature is 77 degrees Fahrenheit, Titan's is minus 289 degrees Fahrenheit, getting close to absolute zero. So there's not much energy on that planet, on that moon, I should say. And basically, there's a liquid cycle, just like on Earth. On Earth, it's water. On Titan, it's methane. So it's liquid methane. Methane on Earth is a gas. On Titan, it's a liquid because it's so cold. And so there are rivers and maybe even oceans of liquid methane that evaporate, become clouds, and then rains liquid methane somewhere else. On Earth, the surface rock, the surface rock is silicon dioxide, like quartz. On Titan, it's organics. So all the surface rock on Titan is organic rock, organic material, carbon-based material. On Earth, the crustal rock, the crust that's lower than the surface, is also silicon dioxide. On Titan, it's water ice. And interestingly, so this is what the artist's conception of what it would look like on the surface. So all of this stuff is organic material that's solidified. And the liquid is liquid methane. But if you look at it, there's this several mile thick liquid water below the crust. And since there's all this organic material on the surface, And we know that there are cracks in the surface crust that could get this, or organic material could get down into the liquid layer on Titan. So that would be a very apt way in which life could start there, for example. We don't know, but because of this, NASA does have a mission scheduled for Titan in the not too distant future, assuming NASA gets its funding. Enceladus is one of the smallest moons of Saturn, but its orbits much, much closer than Titan does. And it does have geysers with ammonia-rich water. So this is, as you see, a nice planet, but you see these geysers here of this, because of this liquid water. But there's some interesting findings recently. First of all, there's large amounts of dihydrogen, which is evidence for hydrothermal vents, just like on Earth. And that would be a source of energy. There's an abundance of carbon dioxide and methane, so organics. And there's new findings of phosphate in the plumes. Now, on Earth, phosphates are used for two things. They're used in DNA, in biologic matter. They're used for DNA, and they're used for energy. Okay, it's part of how you are able to do this. So there's a possibility of life on even Enceladus. So NASA does have plans for a flagship mission sometime in the future called the Enceladus Orbalander, where there would be a lander to land on the surface of Enceladus, looking at the surface, but also an orbiter to look at the overall surface. Callisto is the second largest of Jupiter's moons. It was originally thought to be a dead world, like just frozen ice and rock, but later probes demonstrated the possibility of an ocean. The only problem is the ocean is much deeper than was thought, or is not present at all. That is just like a slurry of ice and water. So again, no plans for a future mission there. And because that's Callisto. And again, this looks like basically an ice world. And you see that there's this thin rim deep down of what they thought might have been water, but either it's deep down or this isn't even real water. It's just like water ice type of thing. But if you look across all of our solar system, there are lots of water worlds, right? Besides Earth, there's Enceladus, Europa, Pluto, Triton. So even as far out as Pluto, there's water deep down again on Pluto and Triton. We're not clearly sending missions there yet, but that might be something in the future. And again, Triton, Callisto maybe, Titan definitely, and Ganymede. So there's lots of possibilities for life in any of these water worlds. And then there's even thoughts about life on Venus. The temperature on the surface, however, is 900 degrees Fahrenheit. The pressure is 90 times that of Earth. So it can melt lead, and if it doesn't melt lead, it makes it squash flat. Okay, so no life on the surface. What about life in the clouds? Well, the clouds are all surface sulfuric acid, but some US orbiters found these dark streaks that they thought could be mats of bacteria, although more recently they didn't think so. They thought it was just radar returns. But there was discovery of phosphine in the clouds. Now on Earth, phosphine happens only in some industrial plants and some bacteria. And there are no industrial plants on Venus. So we're looking at the possibility of looking for life in the clouds of Venus. Is a life there now? Well, clearly not on the surface, as I said, but what about the clouds? Well, 30 miles above the surface, you have better temperatures. It's 86 degrees Fahrenheit to 158 degrees Fahrenheit instead of 900 degrees. And the pressure is similar to that of Earth. Well, still some problems because if it was bacteria, let's say, they'd be floating in the atmosphere. There's no significant water. It's only trace amounts of water. And there's sulfuric acid in the clouds, and that strips away DNA and proteins. But I keep giving you buts, I know. In Earth, there's lots of bacteria that do float in the clouds. And basically, as they're in water droplets, as the water droplet enlarges, it rains and washes the bacteria out. But then they're picked up again when they evaporate. In Venus, the sulfuric acid droplets might enlarge with bacteria. The bacteria form spores. Winds may then carry them back up into the surface clouds. So it'd be something like this, a cyclical type of phenomenon, where you have the bacteria getting washed out, they form spores, they get back up, etc. And what about the lack of persistent water? Well, there may be other solvents that support life. And scientists believe there may be some small amount of water in these sulfuric acid droplets that it would allow for bacteria to survive. And some bacteria have actually adjusted to highly acidic environments. There's some that are extreme acidophiles in highly acidic areas with pHs less than 2. For example, these species are all Thiobacillus. Now, look at all those colors. Where have you seen colored water like these colors where the pH is less than 2? Yellowstone. Those pools in Yellowstone are filled with these bacteria. That's what colors them. The bacteria survive there in pHs less than 2. And they handle it in 2 ways. They have a proton pump that pumps out the acid and pumps in bicarbonate. So it maintains a neutral pH inside the cell compared to the outside. And it secretes a waxy layer to protect the cell. So could happen on Venus as well. So then we have to ask the question, how did organic material, now you can say carbon, but how did organic material, organic molecules get to Europa, Titan, Enceladus, Venus, Mars, and Earth? I mean, it sure doesn't look like it started on Earth. There were experiments trying to see could life, or at least the molecules that lead to life, happen if you took a bunch of carbon goo, put an electric arc through it, and nothing happened. It still had carbon goo. Okay, so how could this have happened where the molecules that are necessary for life got to Earth or got to Mars or any of the other planets or moons? There's 2 new updates. One is this Japanese spacecraft called Hayabusa 2. It explored this asteroid Ryugu from June of 2018 to November of 2019. And it returned a sample of the, asteroid, not comet, about 5 grams worth. So a tiny little sample. But in that tiny little sample was this character, uracil, which makes up part of RNA. Okay, not DNA, but RNA. And a lot of scientists, biologists think that possibly life started with this simpler form of RNA, which then got swallowed by a cell that was making DNA so that the RNA could become messenger RNA. So maybe one of these asteroids did that, but they only found the uracil. That doesn't mean a lot because you still need the other bases to make up even RNA. So we're still shrugging our shoulders. Well, along came OSIRIS-REx. Its origin was to return and analyze a sample of a carbonaceous asteroid. And this was what they did. It was this spacecraft, and it put this thing down onto the asteroid, blew out some nitrogen gas, so all this grainy stuff would come up, get caught in here, and it could take the sample back. Well, the truth of the matter is it didn't just land on it. It dug into it because the rubble was so tenuous. And it took back, instead of the expected 60 grams of material, it took back 250 grams of material. So this is Bennu. That was a target. It was a small asteroid, only about a quarter of a mile in diameter. But we do know that it formed out beyond Mars because it still has ammonia on its surface. From when we got back to sample and from spectroscopy examining it, it had a lot of ammonia on the surface of the asteroid. Now, ammonia is volatile, so if it formed near Earth, it would have all been boiled off, and that didn't happen. It stayed on the surface of the asteroid. This is basically the plaque outside the sample return mission lab. This is the lab. It's all completely sterile. The only way they handle the sample is with these glove boxes. So in a sterile environment and a nitrogen-filled environment, so nothing can interact with the sample. Okay. And this is the sample that was brought back. These are the 250 grams of material that were returned. So they've been analyzing this, and what they find. Two things. Does anybody recognize these? Amino acids. These are the 20 amino acids that are required for human life. You have to ingest these 20 amino acids to be able to live. The sample that was brought back, 14 of them, 14 of these amino acids were on the surface of Bennu. Even more interesting, does anybody recognize what these are? Nucleotides. You know which ones they make up? Both RNA and DNA. All of them were on Bennu. All of them were on Bennu. All of them. When they examined it. So this is the starting blocks of life. Now, does that mean there was material? Was there life on the asteroid? No, not likely, because it was just floating around in space. There's no energy. It's not going to form life on it. And there was no liquid water, certainly. But in summary, there's no evidence for intelligent life, but there's so many planets in the universe it's likely, and we're still looking. There's no definite evidence of any life in the solar system, but lots of planets and moons are habitable conditions. And now we're getting hints that there could be life on these planets. So we're likely to find life somewhere in the next 20 years. and I'll answer any questions anybody has.
Get a mic for questioners.
And we can turn the lights back on.
Dave, will you do the honors and pass the mic around?
Do people want a 5-minute break, or you're okay just going into the question?
We'll do away with the mic. People can get up, go to the bathroom, or get coffee. Charlie has the first question.
Thank you, Dr. Magnificent briefing. All of your discussions centered on human life forms. Are there considerations for other types of life forms beyond human?
Oh, absolutely. I didn't mean to insinuate. The life we are mainly looking for is any kind of life, and the likelihood is what we're going to find within the next 20 years is either bacterial life or perhaps maybe multi-celled early type of life.
Perhaps ask my question that way. Carbon-based life versus other forms of life, like silicone.
Yeah, we're not looking for Horta yet, and anybody who's a Star Trek fan knows what I'm talking about. Is that possible? You know, it's theoretically possible. We wouldn't, you know, we're looking for. You still have to have some kind of medium to have and energy. So we're not necessarily looking for carbon-based, but that's the likelihood of what we're going to find. But yeah, should we come across something that is not carbon-based? Sure, we'll look at that.
Doctor, thanks for the presentation. Very interesting. One editorial comment: as a guy from a generation that was raised on Lost in Space and Star Trek, it's very easy to, when you say, is there life on other planets, to think of something humanoid with a square, shaped head or something like that. But truly, that's, we need to be better informed, and obviously from a scientific standpoint, that's what you're looking at. But a specific question, you mentioned, and excuse me if I get this wrong, you mentioned that they detected the presence of dimethyl sulfide from the Webb telescope. And I'm curious, how were they able to measure or determine that was there?
Spectroscopy can do that. The way spectroscopy works is basically the light coming off of a planet or star or whatever. Is you can break it down into its individual components. Okay, and based on that, you can find what each molecule vibrates in a different area. And so dimethyl sulfide has a certain characteristic to it that you can see based on its spectrographic analysis. And don't ask me to explain it any further, because I'm not an engineer.
Thank you. It's wonderful. It raised us from our humble problems here on life to a larger view. About 20 years ago, my company developed at Huntsville the flight plan for the trip to Mars. And can you tell us about the plans for the trip to Mars, when and how it's shaping up?
So it depends on whether you're talking about the flight to Mars, that would be the lander, just to an unmanned lander to be able to collect the samples, or if you're talking about the manned mission to Mars. So we're not near either of those yet, mainly because of funding. The original plans for the unmanned lander was a NASA plan. that NASA was going to do it. Then NASA had some of its funding cut, so it became NASA in partnership with one of the commercial enterprises, SpaceX, Blue Horizon, one of them. The funding has been further cut so that NASA now has no plans for the return mission in terms of returning the samples back, and is looking to partner completely with hopefully a commercial enterprise that steps up and says, we'll do it. Whether that will happen or not, I don't know. It's going to depend on how much funding NASA gets and how much the commercial partners want to engage in this. So we're sort of at a standstill now. We're still hopeful, though, that it will happen by the 2030s. For the manned mission to Mars, NASA is still doing preparatory work towards that goal, figuring out, can people live together for 3 years in a tight environment? Can they be protected for 3 years from radiation, et cetera? So they're still investigating that. But the actual flight, again, we'll have to see what happens.
Is there any way to, like for example, in the exoplanets in the TRAPPIST system, to determine whether they have a magnetosphere? I know the one on Earth protects our environment from radiation and particles from our sun. Is there any way to do that to those exoplanets? Is that something that NASA's looking to in the future?
The answer is exoplanets are light years away. So there's no way we can send a probe. It would have to be by telescope, and there's no way by telescope to see if a planet has a magnetic field, unless you see an aura somehow on the planet. And what you get from a planet is a little dot. So they're not going to be able to. The only other way of seeing it is by liquid water on the surface. And if there's liquid water on the surface, it's likely that they have a magnetic field, because it otherwise would have been boiled off.
I know that limits what could happen on Mars now because of the radiation, because it no longer has an active.
Right. Mars did have an active magnetic field at one time, which allowed it to have water on its surface. Why that, and the fact that the magnetic field went away is why the water boiled off. But why the magnetic field went away, no one knows.
Thank you. That's a great talk. I have just kind of a fundamental question. What does NASA consider? I understand. What does NASA consider life? You know, because I know from origin of life studies, you know, that the life can be considered many things. Many people are actually trying to define what life is. I know we have organic life or carbon-based life, but what does NASA consider life?
So I don't know what NASA's official statement about what is life. Something I have to ask one of their astrobiologists, which I might get a chance to do. But I can tell you that basically the definition I knew of was being able to engage in metabolic processes to be able to sustain itself, and be able to procreate, i.e. reproduce itself. And those two things are the most important things that define life. So whether NASA has a different view of what life is, I don't know. And that's a good question. I'll have to find out.
Would you consider that life kind of intelligent or displaying intelligence?
No. As I think I hopefully showed you, NASA is looking for any kind of life, from bacteria on up. So yeah, if we find something more, more like us, that'd be great. But even finding life of any kind somewhere else indicates that we are not alone in the universe. We're not the only planet to have life. And that's I think, an important philosophical question that could be answered.
Doctor, thank you for a fascinating talk. With present technology, how many light years out can we be effective in determining the things you were talking about?
So how many light years out? Well, probably within a few hundred light years of us. When you get beyond that, the James Webb Space Telescope can see all the way back to 400 million years after the formation of the universe, but it only sees small specks for whole galaxies. So you're talking about only our galaxy can we look at, and only our area so only our arms of the galaxy can we look at. So a few hundred light years out, but there are plenty of stars in those few hundred light years.
Hi, I just wanted to share a thought about life. When I was not pre-med when I went to medical school, so I was always learning new things like ATP is actually part of the DNA sort of setup. But the bottom line of this is, what is life? I hate to bring up this word, wall, W-A-L-L. A wall that keeps the cell within itself. It would seem to me that's a big part of the definition of life. And the main thing about that wall is the inside goes outside, and then the outside is inside. I mean, it's essentially like, unlike, like. I'm sorry, like, unlike, like.
So that's a good point, and you have to look at it not as a wall, but as a barrier, because, for example, animal cells do not have walls; they have membranes. It's only bacteria and plant life that have cell walls. But that's a good point, and yeah, certainly you have to be able to contain the processes to be able to metabolize within a unit, and that requires either a wall or a membrane.
Ask a question of the point you brought up about the frozen ocean bottom, where ancient crustacea survived. The continents and the oceans have changed over the millennia, and usually various animal forms have changed and evolved depending on those changes over the millennia, which also had climate changes. I would think, would you not agree, that the animal forms evolved to change with those changing oceans, changing continents, and changing climate, rather than developing a completely different life form?
So that's a good point. I'm not an evolutionary biologist, but my understanding is that basically when they look at the forms that are there, they took samples from down there and looked at them, looked at the DNA, looked at the things that were there, and they see differences where they can't link it to anything that past or present on Earth. For some of them, not all of them, but some of them. So at least some of them had to have developed down there.
Well, thank you very much, Doctor, for a fascinating presentation. couple of points, next month, we have Jen Kidrick, CEO of the Air and Space Museum, who will be here June 27th. So please plan on attending that. That should be fascinating also. But thank you very much for your presentation to us.